Okay, one problem completely down, one problem kind of down, as in we know the answer to this in some sense. We got it from a calculator, but it does ask us to evaluate the showing steps. We've done problems like this before, and you may sort of like tighten up a bit, like in your back muscles, just when you see absolute values, because as we've discussed before, to be so nice intuitively, they seem to be a real bother every time we've got to deal with them analytically. All right. So when we've seen this before, we had to use that splitting property of definite integrals to break this up before we could go about trying to use the fundamental theorem to come up with a solution to this thing. Like, for the record, this happened on the test. Don't just tell me that this is x squared plus 7x evaluated at each endpoint and take a difference. That doesn't work. You can't like pass that integral through those absolute value bars. That doesn't cut it. So we've got to split this thing up at that corner where the absolute value function touches down on the axis. So you can find that by setting this equal to 0. It's negative 7 halves, negative 3.5, however you want to write it. So I'm going to break this into two pieces. So now, from negative 6 until we get to the breakpoint at negative 7 halves, what's inside here is going to be negative, right? Like if you plug in negative 5, you get negative 3 back. So to take the absolute value of something that is already negative, we negate it. Thus the minus sign right there. All right. So on the other hand, when we go from negative 7 halves to 1, what's inside here is already positive, so we can just kind of chuck the absolute value bars completely. So, all right. Now, each of these guys we can evaluate using our buddy, the fundamental theorem of calculus. So this guy here, our antiderivative, is x squared plus 7x with a minus out front. So negative x squared minus 7x, negative 6, negative 7 halves. Right here, the antiderivative is the same thing, just without the minus. So x squared plus 7x, negative 7 halves, 1. All right. So now, remember, we evaluate our antiderivative here at each of these endpoints and then take the difference. When I plug negative 7 halves into this thing, I'm just going to write it as a decimal, so just to save board space. So I got 12.25. When I plug in negative 6, I got a positive 6. So we have, remember, the fundamental theorem calls for a subtraction there, so 12.25 minus 6. This plus is built in thanks to our splitting property. All right, I plug in 1 squared plus 7 times 1 is 9. Sorry, not 9. It should be 8. I messed up. So that should be 8. When I plug in negative 7 halves, I get a negative 12.25. So, all right, now pounding out all the arithmetic, these work out together because this is like an addition. You get 24 and a half minus 6 plus 8. Lo and behold, that is the 26.5, or I guess 53 halves if you want to go fraction, on this. So that's how we would get this analytically. Like I said, absolute values always seem to end up having this effect on people. So that was technically problem 10. All right. So up next, I want to take a look at the most requested problem, in terms of what to look at as far as review solutions. It's an application problem, and it's one we've talked about a fair amount. So let me clean this up, and then we'll get started. Okay, so problem 15 asks us for an equation for a line tangent to the graph of this thing at a point with a particular x-coordinate and y-coordinate, 1, 2, for what it's worth. So this comes back again. We saw this an awful lot in chapter 2, and I like to bring it back up because it is sort of like the archetypal example of why people were doing calculus problems in the first place. So remember, derivative and tangent line slope, not tangent line equation, slope of tangent line and derivative value are in fact one and the same thing. If you go back and look through your notes, you'll see the circle of calculus where I link that up with rate of change kind of stuff as well. So in order to get our tangent line slope, we need our derivative. In order to take a derivative of one of these is a little easier than the other. This is just a power function. We can use the power rule. This here is a product. Hopefully you remember, we need the product rule in order to work that thing out, right? Right. So derivative of our first piece of the product, 4x, just gives me 4. times ln of x left by itself, plus, now I leave the 4x alone, and I multiply that by the derivative of ln of x, which our bestest friend sheet tells us that's 1 over x. 2x cubed, that one's not too painful. We use the power rule. Hopefully that seems okay at this point that you get 6x squared. So there's our f prime of x. So the tangent line slope that we need, m, tan, if you will, is the value of our derivative at the target x coordinate, which was 1 according to the problem. When I plug 1 into all of this stuff, well, the natural log of 1 is 0. Those two cancel out, so we've got 4 plus 1 squared. So it looks like our slope should be 10. All right, so now we've got a slope. We were given a point. We can plug those into our point-slope form to get an equation for the tangent line. So we have y minus our y coordinate of 2 equals 10, our slope, times x minus our x coordinate of 1. That's the point-slope form. You may prefer to write it in the slope-intercept format. If I distribute the 10 and then add over the 2 that's sitting here, we get 10x minus 8. I like the slope-intercept. I wouldn't have killed you if you'd left it in point-slope form, unless the problem specifically says put it in slope-intercept form. So that's what we got here. Like I said, it's our classic example, and but it's been a while, so I get why you might want to go back and take a look at it. All right, so that's 3 of our 4 most requested problems down. I need to clean the board off one more time, and then we'll take a look at the last one, problem 20. Okay, I kind of get why people would pick problem 20. It's not necessarily that any one bit of it is hard. There's just a lot of it. Inside baseball here, but this problem used to be multiple test review problems that we just kind of mashed together into one big derivative calculation. So I'm actually going to break this apart into individual pieces so you see in the review packet that g of x is this big long multi-term thing. I'm going to deal with stuff bit by bit as it comes up. So the first 2 terms, the big issue here is making sure you do the algebra to convert them correctly. So that's 5x to the negative third up front. Square root of x is 8x to the 1/2. So the derivative of that piece, so the derivative, I feel compelled to write this out. It's not just g prime of x in this instance, because I've grabbed out like one segment. But, so the derivative is negative 15 x to the negative 4 from the power rule there again. So there's, that part we could untangle the exponents. That's kind of the first bit of this. Up next, we've got 3x plus 2 over 4x plus 1. That is a quotient. We need to use the quotient rule in order to, break this thing down. So for what it's worth, I'm labeling this in parts, even though it's not that way. Your final derivative would be this stuff plus the derivative of this. Hopefully that makes sense. All right. So our derivative here, like I said, we need the quotient rule. We square the denominator. That's 4x plus 1 quantity squared. The formula for the quotient rule coming up top, we get our denominator, 4x plus 1, times the derivative of the numerator. That's 3. Minus, now we take the derivative of the denominator, 4 times the numerator, which we leave alone, so 3x plus 2. All right, so we smash out the algebra here, distribute the 3, distribute the 4, combine like terms. As it turns out, that collapses down pretty nicely, so we'd end up with just negative 5 over 4x plus 1 squared. Okay, so that's the first 3 terms of this thing. I'll deal with another term in just a sec here. So we have 5 over 3x. You could use the quotient rule. Don't. That's 5/3 times x to the minus first. If we pull that up top, it's really just more algebra, kind of like we did here. So we have negative 5/3 x to the negative second out of that chunk. So that's the first 4 terms. We've got 2 left to take a look at. I'm out of board space. Give me just a sec. Okay, the next term in problem 20 asks for the derivative of 3x squared sine of x. We kind of just did this, right? It's a product. We need the product rule. So So we need the product rule. Okay. Derivative of this guy, so that would be 6x sine of x, plus, now we leave 3x squared alone, and then take the derivative of this guy. Our bestest friend sheet says the derivative of the sine of x is positive cosine of x. It's not an antiderivative. Don't try tossing in a minus. All right, so now, e of this guy has 5 times 3 minus 2x cubed. You could do this the algebra way, smash out what happens when you cube this. Don't go there. Use the chain rule. So, all right. So, our outer function in this case is the cube. The inner function is the 3 minus 2x. So our buddy, the chain rule, says we take the derivative of the outside function without touching the inside. The 3 hops out front. So 15 times 3 minus 2x. This exponent needs to go down by 1. And again, if you need to do like the u sub thing, that's fine. I'm just short on board space and time because I want to wrap this video up. So the catch is the chain rule still says we've got to multiply by the derivative of what's living inside here. The derivative of that thing is negative 2. I would rearrange that to negative 30 times 3 minus 2x quantity squared. Okay, so now we've got all of our individual pieces. I will go ahead and write them up on the board in one big line, but you're not going to watch me write that out. I'm just going to combine them all and say, ta-da! So hold on a sec. Ta-da! Anyway, so here's what your derivative looks like when you put together all of the individual pieces that we just worked out. So if you'd like to clean up the algebra a bit, you can undo these like negative exponents and stuff. It's not strictly necessary. My big thing here is making sure you know how to do the calculus. I know this problem is really long, but it really does cover like all of the derivative rules we've talked about kind of in one swell swoop here. So yeah, that's why I'm kind of okay with how massive this thing is, because it covers it all at once instead of us having like 3 other problems where, oh, here's where the product rule is needed. Oh, here's a quotient rule problem. Oh, here's a chain rule problem. Unfortunately, real life is way less likely to hand something to you like that. So those are our solutions to the 4 most popular exam review questions. As promised, I will be posting solutions into Moodle that are written out. It's just this is where the video content's going to come to a close. So you see this? Act like it's a mic. I just dropped it. We done.